Hello, and welcome to the AWS series on automating infrastructure deployment and website hosting with Terraform, GitHub Actions, and AWS. This series demonstrates an advanced application of DevOps practices and tools to automate the deployment of cloud infrastructure and a static website. Utilizing Terraform for infrastructure as code, GitHub Actions for CI/CD, and various AWS services, it demonstrates a streamlined process for setting up a secure, scalable, and efficient web hosting environment. The CI/CD pipeline implemented with GitHub Actions includes jobs for deploying your infrastructure using Terraform, syncing your files to an S3 bucket, and invalidating your CloudFront cache. So, when you make changes to your website, commit your updates, the pipeline automatically handles deployment and content distribution. This series involves a progressive approach to cloud infrastructure development, utilizing Terraform modules to systematically build and enhance a comprehensive web hosting solution. Starting with the configuration of a remote backend for state storage on AWS, the series evolves through successive stages. Each stage introduces a new component, from securing connections with SSL certificates, hosting a static website on an S3 bucket, to ultimately distributing content globally via CloudFront. This modular, build-upon strategy demonstrates the power of infrastructure as code and showcases how each element interconnects to form a secure, efficient, and scalable web hosting environment. My name is Deniz Yilmaz, and I'm an AWS content creator. Feel free to connect with me to ask any questions using the details shown on the screen. Before I give a deep dive on the architecture, let's first outline the objectives. First, you'll be setting up the development environment. Then, you'll configure the Terraform AWS backend module. Next, you'll automate the deployment with the GitHub Actions CI/CD pipeline. Then, you'll develop the DNS and SSL certificate management module. Following that, you'll create the Amazon S3 static website module. You will then implement the Amazon CloudFront distribution module. You'll deploy and manage all the infrastructure with Terraform. And finally, you'll implement security and adhere to cloud architecture best practices. If you refer to the video description below, you will find a link to the Codebase repository. Here, you will find a selection of Terraform module templates, complete with predefined resource blocks, which have been compiled for your convenience. The tasks at hand will involve filling in the attributes and defining the variables and outputs to meet your unique infrastructure needs. The Codebase also includes pre-configured GitHub Action jobs. These ready-to-use jobs are designed to automate essential tasks such as seamless website deployment. Should you not possess the necessary website files, this Codebase is fully equipped with all the essential website components, including HTML and CSS, so you can get started. You can customize the information within the HTML file to accurately reflect your personal details and social media links. Additionally, for a comprehensive view of the completed project, including the finalized Terraform modules and GitHub Action jobs, you can access the completed repo by referring to the video description below. For this project, you will need the following toolset: an IDE such as Visual Studio Code for writing and editing code, a GitHub account for hosting the repository and managing the CI/CD pipeline through GitHub Actions, Git for a version control system to track changes in the source code, an AWS account to access AWS and to deploy and manage the cloud resources utilized in the series, the AWS command line tool for managing AWS services, necessary for configuring and managing resources directly from the terminal, a registered domain name with Amazon Route 53, necessary for setting up DNS records, Terraform, an open source tool for building, changing, and versioning infrastructure, the tree command, used for displaying the directory structure of the series in a graphical format, the touch command for creating empty files, available by default on macOS and Linux. Windows users can achieve a similar functionality using PowerShell by running the new item command. Let's now take a closer look at the solution you're building, examining each part of the system to understand how it all works together. In part 1 of the series, you begin by creating a new repository on GitHub. This repo will serve as the central hub for your website's code, Terraform files, and the automation workflow. You'll then clone this repo to your local computer and then work on this project in Visual Studio Code. Moving on, you'll structure your Terraform project by establishing necessary folders and files. You'll first create a dedicated folder to house your website assets, and then copy your website assets into this directory. You'll set up a Terraform folder along with a nested modules folder to organize your Terraform configuration files. This approach promotes a modular and easily maintainable code structure. Within this structure, you will create the essential Terraform files, including a main configuration file for running Terraform commands, a backend Terraform file for specifying state management, an outputs.tf file for defining output variables, a variables file for declaring input variables, and a terraform.tfvars file for assigning values to these variables. You'll then wrap up part 1 by committing these files to GitHub and ensuring that your project's progress is tracked and ready for the subsequent tasks in the automation process. In part 2 of the series, you'll focus on the creation of a remote backend module. You'll configure the necessary AWS resources that will support a Terraform remote backend. Within this Terraform module, you'll incorporate 3 important resources. First, you'll establish an IAM user dedicated to Terraform. This user will come with the essential permissions required to effectively manage your infrastructure. While creating an IAM user for Terraform isn't required for a remote backend, using a dedicated IAM user for Terraform provides a clear audit trail, simplifying the tracking of Terraform's actions in AWS for better compliance. Next, you'll create a dedicated S3 bucket designed to securely store your Terraform state, ensuring the safekeeping of your infrastructure's state information. To manage access to the S3 bucket, you'll define an S3 bucket policy. This policy will outline the permissions necessary for the Terraform user, granting them the ability to perform actions such as listing, retrieving, and storing objects within the S3 bucket. And finally, you'll introduce a DynamoDB table which locks the state file during changes, preventing conflicts among team members who may simultaneously work on the same infrastructure configuration. In the variables.tf file, you'll define several variables to allow customization and flexibility in your Terraform module. The IAM username variable will set the name of the IAM user. The bucket name will define the name of the S3 bucket for state storage, whilst the table name will specify the name of the DynamoDB table for state locking. After configuring the backend module, you'll then integrate it with the root module's main configuration file. But first, you'll define the necessary providers for Terraform, beginning with the AWS provider. Within the AWS provider block, you'll configure essential settings like the deployment region, which is dynamic and set via a variable, offering flexibility when running Terraform. Next, you'll proceed to integrate the backend module, which sets up the IAM user for Terraform, S3 remote backend, and DynamoDB for state locking. You'll provide the necessary variables to the module, allowing you to customize the resources it creates. This modular approach streamlines the process of setting up your Terraform backend and ensures consistent, reusable, and manageable infrastructure code. You'll then also add configuration values to your terraform.tf files file for specifying the region, IAM username, bucket name, and table name. By providing these values, you ensure that your backend module can use them to correctly configure the S3 backend and DynamoDB table for your environment. After module creation, you'll run Terraform init to prepare the working directory, and then Terraform apply to deploy the resources. Following that, you'll then configure and transition to an S3 remote backend. In the backend.tf file, you'll specify the Terraform backend using the S3 bucket and DynamoDB table you've just set up. This configuration ensures that your Terraform state is stored remotely and is lockable for safe concurrent use. After updating the backend configuration, you'll run Terraform init to initialize the new backend, connecting to the S3 bucket and DynamoDB table. With the remote backend module and main configuration file in place, you'll wrap up part 2 by committing and pushing these changes to your GitHub repository. In part 3 of the series, you'll then set up a GitHub Actions CI/CD pipeline to automate deploying a static website to AWS with Terraform. The process begins with organizing your repository, creating a GitHub directory for your GitHub-specific configurations, and a workflow subdirectory to store the pipeline files. This structure allows GitHub Actions to automatically detect and execute your workflows. Your workflow file, triggered by pushes to the main branch, outlines a series of operations: checking out the code, setting up Terraform, and running commands to format, initialize, validate, plan, and apply your Terraform configurations. You'll then utilize GitHub Action Secrets for secure management of AWS credentials and Terraform variables, enhancing the security of your automated CI/CD pipeline for deploying to AWS. The automated pipeline ensures that any changes pushed to your codebase are reflected in your AWS infrastructure, maintaining consistency and streamlining deployments. In part 4 of the series, you will create and deploy an AWS Route 53 and ACM Terraform module to secure your website. This Terraform module configures a public SSL certificate for a domain using AWS Certificate Manager. It then creates a DNS record in Route 53 for the certificate's DNS validation. Once Route 53 validates the record, the SSL certificate is confirmed and ready for use, ensuring that the domain and subdomains are secured with HTTPS. In this module, the variables file sets the domain and TTL configurations, and the outputs file outputs the SSL certificate ARN, Route 53 zone ID, and the root domain name. These outputs will be used as inputs in the CloudFront module when setting up a CloudFront distribution in part 6 of the series. After writing the main code, you'll then integrate the module with the root module's main.tf, and then you'll deploy the complete configuration through the CI/CD pipeline established with GitHub Actions, which will utilize Terraform's automation for a secure and efficient deployment process. In part 5 of the series, you will create a Terraform module for setting up an AWS S3 bucket specifically designed to host a static website. This module handles the creation of the S3 bucket, configuring its versioning to keep a history of changes, setting up the website configuration to specify the index document, and managing public access to ensure the website is accessible to internet users. Additionally, you define a public policy to allow public read access to the website's content. The variables for this module include the bucket name, whether to force destroy the bucket, versioning status, the index document, and the AWS region. Outputs are provided to retrieve the S3 bucket ID, ARN, the website URL, the index document, and the bucket regional domain name. These outputs will become useful when integrating with the CloudFront module and for verification and reference. After creating the module, you'll enhance your CI/CD pipeline with a new job to sync your website files to the S3 bucket. This job runs after the Terraform job and uses GitHub Actions to sync your files. It relies on the AWS secrets for secure access to your S3 bucket, ensuring your static website content is up to date with your latest repository changes. In part 6, and the final part of the series, you will create a CloudFront module for secure S3 content delivery with SSL. You will connect the CloudFront module with your existing infrastructure by incorporating details from the S3 website and DNS ACM modules. This integration ensures CloudFront correctly utilizes the designated S3 bucket and SSL configurations for secure and efficient content delivery. The module includes setting up a CloudFront distribution with an S3 origin. This means your files are stored in S3 and delivered via CloudFront, which caches content for faster access and improved performance for end users. You'll set up a CloudFront origin access control resource. This is a security feature that restricts access to an S3 bucket's content, ensuring that it can only be accessed through CloudFront, which enhances security and utilizes CloudFront's performance benefits. You'll also set up IPv6, default root object settings, and establish a specific S3 bucket policy for CloudFront. And then finally, you'll create a Route 53 alias record to link your domain to CloudFront. This directs your domain's traffic to the distribution. You will use variables instead of hard-coding values. You'll then create an output that provides the ID of the CloudFront distribution, which will then be used when setting up a job that invalidates your CloudFront cache. This job, named Invalidate CloudFront Distribution, will run after the S3 sync job, and it uses a GitHub action to invalidate the CloudFront cache. This ensures that any changes to your website are immediately reflected, keeping your content up to date for all users. After finalizing the module and integrating it with the root module's main.tf, you will initialize Terraform in your local workspace and commit and push the CloudFront module to GitHub, and then monitor the GitHub Actions workflow to deploy the resources automatically. The AWS Well-Architected Framework is designed to help cloud architects build secure, high-performing, resilient, and efficient infrastructure for their applications. It's built around 6 pillars: operational excellence, security, reliability, performance efficiency, cost optimization, and sustainability. Let's see how this series aligns with each of these pillars. The objective of the operational excellence pillar is to achieve effective operation of workloads through automated deployments, monitoring, and iterative improvements. This project uses CI/CD pipelines for automation, ensuring consistent deployment practices and reducing human error. GitHub Actions automate the deployment process, enhancing the ability to monitor and iterate on infrastructure with minimal effort. The objective of the security pillar is to protect information and systems by implementing strict access controls, data encryption, and regular security assessments. By using AWS IAM for access management, AWS Certificate Manager for SSL, TLS certificates, and strict S3 bucket policies, this series ensures secure access to resources and encrypted communication, adhering to best practices in cloud security. The objective of the reliability pillar is to ensure a workload performs its intended function correctly and consistently when it's expected to. This includes the ability to recover from infrastructure or service disruptions. By utilizing AWS S3 for durable storage, DynamoDB for state locking, and Route 53 for DNS management, all enhances reliability. These services ensure high availability and fault tolerance, critical for maintaining consistent access to your web application. The objective of the performance efficiency pillar is to use computing resources efficiently to meet system requirements and to maintain that efficiency as demand changes and technologies evolve. The series optimizes performance by using AWS CloudFront for content delivery, ensuring low latency and high transfer speeds globally. The use of Terraform allows for easily scalable infrastructure, adapting to varying loads efficiently. The objective of the cost optimization pillar is to avoid unnecessary costs by managing resource usage and spending, ensuring that you pay the lowest price for what you use. Through infrastructure as code, the series precisely provisions only needed resources, preventing over-provisioning. Automated resource management via Terraform and GitHub Actions minimizes manual oversight, reducing operational costs. And finally, the objective of the sustainability pillar is to reduce the environmental impact of your cloud workloads by optimizing resource usage and selecting efficient services. By automating infrastructure deployment and using scalable, efficient AWS services, the series minimizes idle resources and optimizes energy usage. Utilizing CloudFront reduces the need for high-powered server-side processing, contributing to a lower overall energy consumption for content delivery. Now, let's get started.